All right, I think I got the audio working now. So just coming back from the lunch. I think I'm going to do a quick little once around the whiteboards with some problems that we did in class today. As a bit of an extra chance for some reps and some practice. So that's what we'll do in this video. That's what I'm going to do in this video. And my suggestion to you is pause. For the sake of time, I'm just going to do the problems quickly. But once I phrase the question, you take a second, pause the video, try the problem yourself, and see if you did it right. So that's all. And just trying to get a working foundation here, being able to change gears from one algorithm to the next and not having it be, oh, I haven't seen that in months. So, all right, so 4 coordinates, name 4 coordinates on this line. Again, you're pausing the video. I'm just going to write the answers. I can see a -4 makes a 0 on this side because 0 times anything is 0. So -4 is a good number to work with because I know how to make this 0. I can make that 0 with a y value of 2. So we say that this ordered pair satisfies that equation. In other words, it works. Okay, and then we're going to use the change in y with change in x. Change in x is 5, so 1, 6, 11, etc. Change in y is down 3, so -1, -4, -7. All right, so there's the 4 coordinates that I asked for. Obviously, you could plot those and get a pretty darn good picture of that linear function. All right, so now fraction practice, as we got to make sure we know how to work with fractions. So I'm going to move the 2 to the other side. Here we go. And I'm going to line up my equal signs. I'm going to multiply my unknown by -3. And then I'm going to divide it by 5. That's what I'm being asked to do. I'm going to multiply the number 4 by -3. And then divide it by 5. And I know 2 is 10/5. Okay, so all you got to do is multiply that times that. And that's going to be your numerator over here. All right. So final answer, minus 3/5 x. Minus 2/5. Yeah, slope-intercept form, decreasing linear function. All right, sine of 11 pi over 6. I'm going to talk about the sine function later in this. Might introduce 1 or 2 new things on the video. All right, sine of 11 pi over 6, so that should be -1/2. All right, in case I'm making a tired fatigue error here, you got your circle. You know that there's 6 parts, each part is 30 degrees. If there's 6 in the top half, then there's 6 in the bottom, which means that 12 pi over 6 is 2 pi once around. 2 pi what? Radius lengths. So this isn't the best looking circle. A little rotator cuff trouble here. All right. Just for the record, 1 radian is about 57.3 degrees. Okay, and if you multiply this by 6, 342 and 1.8, 343.8. If you multiply this by 6, you get 348, I believe. That's pretty close to once around the circle. It's pretty close to once around the circle. Yeah, 1 radian, but it takes 6.28 radians. So if I put the 2.8 there, I'd probably get real close to 360 even with that approximation. All right, I need an eraser. All right, so what you were supposed to do was to get 11 of them. You might still be walking around counting on the finger technique, as in 7, 6, 7, 8, 9, 10, 11 is here. All right, perpendicular to the x-axis. 30-degree reference angle, that's got to be 60 degrees. We should know our heights and our widths. Hypotenuse is 1. The height is -1/2. That's the opposite side to the reference angle. Opposite of the reference angle is the sine function. Ask you to memorize sine, cosine, and tangent. If you haven't memorized it yet, you are behind. So opposite over hypotenuse, -1/2 divided by 1 is -1/2. All right. Yeah, I'll mention one thing about the sine function here. And then I think at the end of class, I'll show you where we're headed with it. So let's just take a smaller circle. That's a pretty good one. Let's draw the x-axis. And the sine function is easier to work with than the cosine because the sine is about heights. So if I'm right here, right, and this is the x-axis, right? If I'm right there and I start drawing triangles, I do believe heights start to emerge. Now that's a coordinate. I traveled a certain circumference length, and that circumference length looks to be about that length. And what has happened? My heights have gone up that much. 45 degrees is famous. So 45 degrees is going to get me that height. I don't know how many degrees I went here. So let me just do the unit circle and then plot those values on a curve, and you can see what the curve looks like. All right, so again, circle, x-axis. Now what I'm doing here for the x-axis is sometimes these are called wrapping functions. Here's a radius length. This is 1 radian, which is 1 radius length on the circumference. And then the circumference, wraps around. And what you're doing is you're unwrapping the circumference, and that's becoming your x-axis. So there is no height. The sine function now, this is the origin, 0, 0. There is no height. When I go to 30 degrees, I'm halfway up. The tallest, the longest the radius gets is 1. So the altitudes never get bigger than 1. And that happens straight up, which is at 90 degrees. So let me look at 90 degrees here. We'll call that 90. 30 degrees was a half. So that's 1/3 of the way, 2/3 of the way. So there's 1/2. You're familiar with 60 degrees. That's √3/2, 0.87. Here's 1 right there, right? So 0.87 and 1. So there's the first 90 degrees of the sine function. Next 90, the altitudes come down. Yes, the altitudes come down. So maybe I should just draw a circle here and say, there's an altitude, 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 altitude. In the first 90 degrees, the altitudes increase, and then they start to come down, and then they head in the other direction negatively. So I get the same kind of trajectory, but a sign change. So there's your sine function. Never gets bigger than 1, never gets smaller than -1, because the hypotenuse is the biggest side of a triangle, right triangle. So none of the other sides can overtake that size. All right, I'm going to use that at the very end of this video to show you where we're headed. It's going to take you a little while to get there, especially in a remote world. Next problem, cosine of -16 pi over 3. Just a reminder, here, pausing the video and trying it yourself. I guess that's pinned well enough. All right, so -16 pi over 3. I'm going to do it in my head and see if I get it right. I think I'm looking at -√3/2. But let's check it out. All right, so I see -16 pi over 3. That kind of reminds me of -15 pi over 3. -15 pi over 3 is -5 pi. And I know that the odd pi's are over on this side. 0, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 5 pi, 6 pi, so on and so forth forever. So I'm looking for cosine, which is going to be the x side, the width side of the triangles. And it's going to be -1/2. So that's my fault. Because now I pictured it. I did the picture in my head. -16 is going this way. So -16 pi over 3 is that drawing right there. Right? And so that's a 60-degree triangle, and it should be -1/2. All right, so I did that much too quickly before without actually picturing it. So I pictured it, and that's your value. Now the cosine is all about widths. Oh, I know what problem I wanted to do. I'll do it right after this one. Yeah, it's all about widths. So what was I thinking? Oh, so let's look at a circle. From here to here, it's the x values, right, that we're measuring. Well, what's that length? That length is 1. So if I unwrap the function, once again, that width is 1. There's no height. I can't draw the triangle, right? But the width is 1. So there's a height of 1. So let's put that as a 1. The cosine function, is part of this right triangle. So let's just look at a right triangle, behavior of a right triangle. So there's, well, I want to do that later. So excuse this. I want to make sure I do that as a separate question. All right, so we'll come back and look at that in a second. All right, what I wanted to highlight before looking at that was just a generic, let's make this 10. Let's make this some y value. Let's make them smaller numbers first here. We'll make this 4. Let's make this, how about 7? Okay. And here's our angle A. And I would like you to find the sine of angle A, cosine of angle A, tangent of angle A. So you're going to go ahead and try that. Think about that and answer those questions. And then we're going to look at the easiest way perhaps to go about this process. All right, so pause the video. There you go. All right, now I start work again. All right, so Pythagoras is all about the square areas. So that square is, area is y squared. I don't know that value yet. I do know this square area. This square area is 16. And according to Pythagoras, these two square areas, I believe, add up. I mean, this is the longest square root. So that's the biggest. This is the biggest area. So I got to add 16 to something. And what do I have to add? I don't need to write that. I just need 16 plus something to add up to 49. Sure looks like it's 33 to me. And that drawing looks terrible. Oh, because I haven't done the square root yet, the area. Okay, so now I want to get back to what the side lengths are. All right, so that's the quickest way to do a Pythagorean theorem problem. It's much harder to work with writing a squared plus b squared equals c squared. Much easier to picture it because that's what it's about. So that was a 7, that was a 4. And if this area is 33, then that is the square root of 33, which is somewhere between the square root of 25 and the square root of 36. So this side actually should be bigger. And I didn't realize that in terms of my drawing. I know it now. Okay, so it's bad drawing. It's too bad. But can we quickly then answer cosine, sine, cosine, tangent? Yeah, I think so. Sine, root 33 over 7 is what you're trying to learn. Cosine, 4 over 7. Tangent, root 33 over 4. That's where we got to get started. Kind of understanding what these commands mean. And that's what it meant for you to do. All right, so why did I put this up here? I guess graphing. So we want to be able to graph these. So I know it's cup shape up. This is what I know. I know I'm on the increasing side for a y-intercept. And I also want to get the vertex, and I know it's negative now, a negative x value, because I'm to the left of 0. So 2 goes into 20, 10, cut in half is 5, so minus 5. I throw a minus 5 in, minus 100, cut in half, minus 59, should be this value. I obviously took a bunch of shortcuts there, because I saw the patterns over time. I began to see the patterns. How did you do this problem? Well, let's see how you might have done it. Hopefully, minus b over 2a kicked into your noggin. Minus b, minus 20 over 2 times a, 4. There's the number negative 5. Oh yeah, we did say that this had a negative 5. Which does mean that your y-intercept is to the right of it if we use the number 0. How do we get the y values of both of these? We use the x values. I plug in a 0, I see negative 9. I plug in a negative 5, and I get 50 minus 100 minus 9. I think you can see why now. Oh, we just highlighted that this afternoon, I think, or this morning. 2 to 1 opposite. So it's got to be the right number. It's the only time that happens. One time it happens. 2 to 1 opposite. X value of the vertex. And I think I forgot what it's minus 59. All right, so that's that. I did this in class. I did it very quickly. I doubt you're going to remember this very quickly, but I also know the roots now. I know when this thing hits a height of 0, at that x value and that x value. You only saw me do it once. Might have been way too fast. But I think in order to get up to 0, you know, heights is 0 are up here. And those are all zeros for heights. I think I got to go up 59 units. I think there's multiplication of 2 in this problem. You better divide by 2. What was I looking for? Oh yeah, there's squaring. I mean, if I put this in graphing form, it would be 2x plus 5 squared minus 59. And I'm trying to set that to 0. So hopefully you can see why I have to go up 59 units to get here. Hopefully that makes some sense to you. Okay, I'm putting something in here. I'm adding 5. I'm squaring. So the order of operations here is add 5 squared, multiply by 2, and then add 5. Oh, and then subtract 59, sorry. Subtract 59. And that's how you evaluate. And when you evaluate a function, you get an answer. Well, I'm getting you your answers for your roots. How am I getting your answer? By doing the inverse operations of each of those in the correct order. The inverse of subtraction, addition of 59, the inverse of multiplication by 2, division by 2. Now the inverse of squaring. All right? I'm doubting a lot of you remember plus minus. Well, we talked about it in class, at least one of the classes, A or B, I forget. And then the last thing is adding 5, so I've got to move the 5 to this side. Well, one of the other questions that we will be studying this term, and I think it's in Algebra 2 as well, is I've got the answers to my equation. There are my roots. It's close to 60 divided by 2, which is 30. Square root of 30 is between 5 and 6. So I've got numbers between 10 and 11 for roots. 5 plus 6, 11, 5 minus, sorry, not between, yeah, one of the roots is between 10 and 11. The other one is 5 minus 5, 0, 5, 0, negative 1 is the other one. All right, so how do I get from my answers back to the original equation? It really isn't all that hard. It's a non-textbook method, but that's my rule in class. You find an easier way, you start to do it that way. So what's the easier way? Well, we want to try to get the roots. Well, that means that I have some function equal to 0. The right side was equal to 0 when we were solving for the root. So I guess I got to move everything from the right to the left. And I'm going to do it in the proper order. So let's see if I can move this up. Well, let's just get it. So addition of 5 on this side is subtraction of 5. Plus minus the square root of 59 over 2. What undoes square rooting? Squaring. X minus 5 squared equals 59 over 2. Oh, what undoes division by 2? Oh, multiplication by 2. 2 times x minus 5 squared. That takes care of the division. And I think, you know what I'll do for good measure? I think I'll subtract 59. Yeah, because I think that equation actually gets me a 0. Now, we worked on binomial squaring. So what is, so let me move this up higher. 2x squared plus 20x minus 9. You square that, you should be able to see where x squared minus 10x plus 25 is coming from. We can certainly see 2x squared. We can certainly see, wait a minute, I made a sign error. Where did I make my sign error? Right, because that did not match up to that. The 50 minus 59 did. So I made a careless error here somewhere. Let me see where I made it. Tired brain here. Minus 5 squaring. X minus 5 squared. Boom, boom. Maybe I did this. No, I didn't do it too soon. X squared minus 10x plus 25. I'm not spotting it. This is depressing. I'm missing up something somewhere. So let me play with this. Maybe I made a mistake here. So that's 2x. 2 goes into 20. 10 cut in half is 5. So this is -5. So -5 should have been +5 as a statement. So there's my mistake. Right? I should have written +5 when I was doing this work here, which means this should have been -5. Okay, so I made a dumb mistake somewhere. I guess on this side. So that should have been -5, which makes this +5, which makes that +5, makes that +5, makes that +5. I don't think it changes anything else. And now we have correctly gotten to that. Okay, so that happens quite often. If you've seen me working on a problem and, you know, getting older here, so fatigue sets in on crunching these numbers. So if I do something stupid and you catch it, don't be afraid to speak up. All right, this is not a Bible. All right, so let's actually practice one more time. 3 more problems to do. So there you go. Okay, should have worked with imaginary numbers in your last class. If you haven't, well, I'll have to put a video out there to show you where they come from, but I'm assuming you've already worked with imaginaries. So what does this equal? 49. Double the product, 14, so doubled is 28i. Squaring that, okay, that square affects both terms. So plus 4i squared, what did we say the purpose of I squared is? It's a sign changer. Okay, so it's going to change the sign of the number in front of it. So that's -4 now. This is 49. What's the rules that govern addition? You have to have like terms. We got a couple of like terms, integers. So this becomes 45 plus 28i. And I'm told by many students that this stuff shows up on the SAT, so it doesn't hurt to do it. I's get, I guess they show up in electrical engineering. Can't tell you much more about it than that. What other types of things are we going to do with imaginaries? We simplify them. So something like 5i to the 23rd. Is there an easier way to write that? And in other words, fewer strokes of the marker. Yeah, there is. And it all revolves around I squared. All based on that. Textbook's going to give you a rule of 4, different kind of rule of 4. I'm not a fan of that because if you can remember I squared equals -1, then you're going to get some good mathematics out of this. All right, so the question is, can I express that number using I squared? Yeah, I think I can. I think I can take I squared and actually do it 11 times. That takes me to 22. I guess multiplying by one more I gets me multiplying by I 23 times. Of course, there's an easier way of saying I squared. It's -1. -1 to the 11th is -1 times -1 times -1. -1 once is a negative. -1 times -1 twice is a positive. If I multiply it by a negative again, that's 3 times negative, 4 times positive, 5 times negative, 6 times positive, an odd number of times negative times I. So -I to the 11th becomes 5 times -1 times I. So obviously your answer is -5i. Okay, it's a little simpler than thinking about this. All right, do you remember how to, you're trying to learn how to write an equation that you see because you got the marker, you get to write what you want. So there's a quadratic. You go pause the video, give it a shot. Maybe, you know, this takes 5 or 6 things to do. How many things does it take to do? 1, 2, I think 4. To me, it's 4 things. The first thing that you have to see is using the vertex. Highlighting that coordinate, that highlights that coordinate. We talked about the minimum area because this is an area statement. X minus 2 squared is all about area. That's an area statement. Well, what kind of area have you generated when you put a 0 into the area statement? What do you get when you put a 0 in there? No, you get 4. You get negative 2 squared. I don't think adding 4 to 67. If I add 4 to 67, I'm up here at 71. I don't want to be there. I want to be at 3. So then the question is, how do you get from 67 to 3? Got to go down 64. So that's why you would write this. I said 4, right? So I'm tired. That's why you're writing that. All right. So let's look at this a little more critically. So let's see, can I stand on my left leg or my right? I'm better standing on my left. I got balance there. So Jim's got the ball. Mr. V's got the soccer ball. Exactly 3 feet high. You know, and I got it right out there. And I'm going to come up and I'm going to kick that soccer ball straight up in the air. And after 2 seconds, it's 67 feet high. And I want to know, when does it hit the ground? So this is a height of 3, 2, I guess that's 4, 3. So it hits the ground 3 feet. 3 feet's probably, you know, much closer. What is the time on the clock when it hits the ground? Because then if I actually did the change in Y or the change in X over this small little amount, I could see if how fast it's traveling. Because maybe I want to jump from a ladder 60 feet, 67 feet high, just to see how fast I'm traveling when I hit the ground. I don't think so. Okay, so write the equation. There it is. And I'm going to fool with this equation now. I'm going to play with it a little bit. We're going to talk about what does it mean. All right, so it's a function. I guess I got to put this on a chair. Now let's put it underneath, see if it works there. Yeah, that works pretty good. Okay, I hope I didn't press escape. Who knows what I just did? Looks like it's kind of cloudy. Did I hit the, we'll hope it's okay. All right, so minus 16 happens to be the value of minus 64 over 4. So if I did this out, I'm going to get minus 16 t squared. I changed to t for time. So I'm doing a function. Instead of f, why don't I say height? The height of the ball based on time, and time is in seconds. So that's minus 16, so that's minus 4. So that's plus 64 t, I believe. Let me make sure for, yep. And then this one here is, where the hell am I? Oh, I got to put a 0 in to find the y-intercept. So if I put, so that's 64, well, we already had it over there, it was 3, right? The initial condition was already given, 0 gave you 3. So I didn't have to actually throw it in here. But if you did, you get minus 64 plus 67, which is positive 3. All right, making sure I'm tired, very tired at the moment, got up at 4. I want to make sure I'm not doing something dumb here. So let's just make sure t squared minus 4. Yeah, minus times a minus positive. There we go. And that, according to physics, has to be. Because what is 3? 3 is what we call the initial condition. What does 64 represent? Yeah, well, you saw me kick the ball, right? And I hit it so hard it went into outer space. Oh, no, it didn't. It came back down. Huh. I thought, oh, let me get rid of this term. I'm sorry. So I kicked it at 64 feet per second. Forever. Goes out. Beyond the field of gravity. Oh, so what brings it back down? Because that's a force, 64 to 1. That's how high the ball is. After 1 second, it's 67 feet. But you know what? It wasn't 67 feet because the minute it left my foot, gravity. That's what this is all about over here. So I hope you can see that we just went towards physics a little bit. I know they work in meters now, but I'm an old guy. So I'm sticking with feet. All right. So why don't you put that in graphing form real quick and see if you can get back to this. One more rep. All right, I'm just going to do it. So we're working here though, seeing if we can get back to that. So I got to do minus b over 2 times a. Sure looks like 2 is the critical number here. Okay, then I guess I want to write t minus 2. And I know that I've got a squaring problem. So I'm going to rewrite this in a way that gives me the information about the vertex. So how do I find the vertex? I put 2 in. 2 times 64, 128. So therefore, this should be half of that, minus 64, without even looking. But we'll put a 2 in, 2 squared, 4 times minus 16, minus 64. So minus 64 plus 128 happens to be 64. And 64 plus 3, yes, it does bring me to 67. And I've already got the A term. Maybe you're getting faster at that now. It's only day 2. Okay, maybe you didn't have so much success last year with that. I don't know. But we got a function in front of us and we can work with it. And I know the roots. Do you know the roots? 267. And I also know that the A term is minus 16, yes? Can you put it together? I know this is 4, 3. It's 3 feet high after 4 seconds. The question is, what's the time there? Well, how do I get to 0? I got to go down 67 feet. I got a multiplier, negative 16. Well, okay, well, I better divide by that. I've got squaring in this problem, right? So I guess I can do it over here. I got to go down 67. So when I set this to 0, I hope it makes sense. I got to get down 67 to get to y equals 0. That's one of the reasons that ends up on that side of the equal sign. Boom. Okay, then, I'm multiplying next in the order of operations here. So I've got to, going backwards, inverse. So I've got to divide by negative 16. And a negative divided by a negative is a positive, so I'm going to do that right now. All right, let's move the equal sign over here. So that's taken care of. I guess I got to do squaring. What's squaring? You heard it a few minutes ago. It's plus minus square rooting. Okay, and that takes care of that inverse operation, and negative 2 becomes positive 2. All right, so what is 67 divided by 16? I can tell you what 64 divided by 16 is. That's 4. And I know the square root of 4 is 2. And 2 plus 2 is 4. So I know I'm around that time frame for when it hits the ground. The question is, how much bigger is the square root of 67 16ths? How much bigger is that than 2? I'm going to guess 0.03. I really don't know. But I got a feeling when you fall 67 feet, the last 3 feet probably don't take very long. Okay, which is why you don't want to experience that. All right, so what else we got? 2 more things to look at, and then you're done. Hopefully it doesn't take you too long to go through this, because I don't want to work you too hard, but I want you paying attention for the 70 minutes you're in here when you're here. All right, so linear function, I guess, quick linear function. 2 gets you an 8, get rid of the 2, bring in the 8, 8 to 9, you went up 1, 2 to 20, 2 to 201, oh my God, 199. Sure looks like I'm going over 199 units before I go up 1 unit. Oh my God, this is almost a horizontal line. It's increasing so slowly. All right, so now I want to show you where we're headed eventually. Don't panic when I show you this. The reason I'm doing it is to connect some synapses in your brain that you probably don't even know are being connected. All right, sometimes somebody puts something and it's like, I don't know, but whether you realize it or not, your brain's trying to sort it out. So here we got let's make an alien planet, okay. So the average temperature on this alien planet, we'll say, is 200 degrees, 200 degrees. And we'll stick with probably the easiest one for you to see so far. Let's do this. Okay, so that's 1 year. They got 4 seasons too. Didn't tell you about that. So they got 4 seasons. Yeah. And let's say that we start with that coordinate, and let's make it, let's say 200. So let's say on day 179, we hit the average temperature for the alien planet year once around its sun. Okay. And let's go here. I'm not expecting you to be able to do this at all yet, but let's say that it takes 30 days. Let's go up 30 days. So what's that going to be? 1, 2, 10, 209? No, whatever, 209. And how hot do we want it to be on this planet? How about we go up to, whoo, it's a nasty planet. Let's go up to 5,000 degrees. Oh, nasty. There we go. We got some funky numbers here. What do I see? Well, I know that my x-axis has to start with these numbers. 179 and 209. I know I got to have that. But you know, trigonometry is not about just any old plain number. It's about converting it into radians. So where is this? Well, I can make it act like 0, start. You know, the starting, well, actually it's 200. 179, 200. Well, no, I'm doing the linear part. Boy, the brain is tired. So that's 0. Where's this? Well, that's in a circle as an angle. I went, I think, to that location. That's the max for heights. I'm doing a sine function here. So where is that? Well, it sure looks like it's 90 degrees. But 90 degrees doesn't fit on an x-axis so well. So it'd be nice if we could get it to be a generic number. So what would that generic number be? Well, I know over here, I know that's pi. Well, that looks like it's pi over 2. So I want 179 to act like a 0 degrees or 0 radians. And I want 209 to act like 90 degrees. Let's see here. I'm just going to write this and see if you can, because I'm tired of talking. All right, so how do you graph this thing? These are the steps. Is there a most important y value? Yeah, it's the average. Am I going up from the average or down to get to 5,000 degrees? I think I'm going up. How much am I going up? 4,980. Of course, this is a trig function, and it's a sine function. In this case, starting from that location, I could do it an infinite number of ways. And so now I have to get the rest of it. Well, the rest of it is turning the number, I should have had those, turning the number 179 into a 0. So that's t minus 179. And how do I get from, I guess I better do this, 179, 0, 209, pi over 2. I'm going to make a linear function off of this table. So how much has it changed from 179 to 2? I think we said 30 days. It takes 30 days to go from 200 degrees to 5,000. Must be a tight little orbit. Got close to the sun. Where was I at? Oh, yeah. And how much did I actually change in terms of radians? Pi over 2. And that's this particular sine function. All right, I'm sure that threw you. I probably shouldn't have done it. But giving you a peek into the future so that we could then talk about the temperature. If we threw this equation into a calculator or a computer, we could talk about any day of their particular solar year and tell you what the average temperature is on the planet. Hopefully they don't have global warming. It's already hot enough there. All right, so that's it. The old man's tired here. Sorry for starting to lose it a little bit, but we'll pick up again tomorrow where we left off.